So that is my talk. Actually, we'll be talking today about how do we make a star on Earth. I am Kunal. Obviously, I come from India. So yeah, mein Deutsch ist nicht sehr gut. And of course, my full name is actually Kunal Dheerajlal Jaswantlal Navalal Soni. We have long names in India, but not to worry. You guys can simply call me Doctor Kunal. Dheerajlal, Jaswantlal, Soni, all right, guys? So, let's begin. This journey all starts in the early 1900s of Switzerland. The OG physicist, Albert Einstein, comes up with one of the most famous equations ever, E equals mc squared. And as expected, it immediately blows off everyone's minds. Now, why was this equation so cool? Well, turns out the equation was suggesting that something as little as 1 gram of matter could be converted into energy as high as 9 followed by 13 zeros amount of joules. In other words, it's a huge amount of energy, guys. All right. Now that combined with the other discoveries of the time about the structure of atom gave rise to what we call nuclear physics. So what exactly is nuclear physics? Well, let's do a thought experiment, all right? If we were to take all the elements in the universe and put them in the increasing order of their weights, we would realize that not all the elements are equally stable. There is one particular element that stands out among all of them, and that is my man, iron. Think of iron like the fittest guy in the atomic gym. All right? Naturally, everybody wants to be like iron. But, that is not the case. If we go at the extreme right of this graph, we'll find some pretty heavy and unstable elements, like my buddy, uranium. And these guys, they keep emitting stuff like alpha, beta, or gamma rays in an effort to shed some weight and try and look similar to iron. This is also what we call radioactivity, by the way. Now, these guys are so unstable that if you throw in a tiny little particle called neutron at these guys, they would immediately split off into tinier atoms, releasing a ton of energy. This reaction is what we call nuclear fission and happens to be the basis of all the nuclear reactors that we see in Switzerland. Now, let's go back to the same graph and go in the other direction. Now, if we go to the extreme left of this graph, we will actually find some rather light elements, like my buddy hydrogen. Now, hydrogen also wants to be like iron. So what does hydrogen do? Well, it can fuse together with other hydrogen atoms in an effort to become somewhat heavier, like iron. And in doing so, it also releases a ton of energy. This reaction is what we call nuclear fusion. And this reaction powers all the stars in the universe, including our very own sun. The only problem with achieving fusion on Earth, however, is you need extremely high temperatures of the order of hundreds of millions of degrees Celsius before you can start for the atoms to fuse together. But if you're able to manage to achieve that, you will have for yourself limitless clean energy. In fact, if you look at the reaction over here, you will see that the fuel for fusion is actually just deuterium and tritium, which is nothing but heavier forms of hydrogen, the same hydrogen that makes up the water that we drink. And the byproduct is helium, which is a fairly harmless gas, right? And on top of that, you have an incredible amount of energy released out of this reaction. This is also the reason why nuclear fusion is sometimes referred to as the holy grail of energy. But, it's not so easy to achieve this on Earth, and for a very long time, making fusion reaction on Earth was almost considered like an impossible thing. But that all changed in the 1950s. Two Russian scientists, or Soviet scientists at that time, came up with an amazing concept. They were like, let's build a star on Earth. They came up with a concept to take the fusion plasma, aka the material that makes up the sun, and confine it in a fusion reactor, in a reactor vessel. And a few years later, they even ended up making the very first fusion reactor Earth has ever witnessed. Like, talk about efficiency. And this is what they called the tokamak. Now, over the next 20 years or so, the world was filled with tokamaks. They popped up all over the world. And fusion progressed at such a fast pace that by 1980s, it was believed that fusion was just around the corner. Now today, 40 years later, fusion is still just around the corner. Well, we haven't really seen much progress in fusion over the past 40 years, but nevertheless, I cannot deny that the tokamak, or the fusion reactor, is an incredible piece of technology. So let's see how a tokamak actually works, right? There are 4 basic steps into building a fusion reactor. The first step is to get yourself a Tory spherical shell-shaped vessel. Now, what is a Tory spherical shell? Well, in other words, it's just a donut. It's a vessel shaped like a giant donut hollow from the inside. Then we inject some deuterium and tritium, the same things, the same fuel, hydrogen-based fuel that we talked about earlier. And then next we heat up this fuel to the order of hundreds of millions of degrees Celsius. And we do that by a bunch of techniques with extremely long and complicated sounding names. So let's just skip that over here. Now you put all these together, your fusion reaction will finally start. Your atoms will start to fuse together, and they will start releasing a ton of energy out. And this energy will expand the whole reaction outwards. Now, you want to be able to like confine the reaction back inwards, in order to prevent any tragedy. And this is something that we do with extremely strong magnets all around the fusion reactor. This way, your fuel can burn at hundreds of millions of degrees Celsius inside this reactor without ever even touching the walls of the reactor. And you will have all that nice, big, clean energy out of this reactor. Big, clean energy, by the way. So, well, that is all good. But then what is the problem? Why haven't we still been able to have fusion energy on Earth? Well, it turns out the biggest problem in the fusion so far is not the fact that we cannot produce fusion. It is that we are putting too much energy inside, and what we actually get out is a tiny little fraction. It's not very efficient. And we would ideally like to reverse this situation. And one way to do that, among others, is to just make the reactor bigger. At least when it comes to fusion, size does matter, guys, all right? So, where are we in this journey? Well, at the moment, we are still just able to show that fusion is indeed plausible, which we are doing by doing experiments in the largest reactor called JET in the UK. And the next step is to show that fusion is indeed feasible, which we are doing at the moment by building the biggest fusion reactor in the world called ITER. And by how big, you might want to focus at this tiny little guy just above the arrow. This is how huge this reactor is. And if ITER is successful, we would move on to even bigger reactors over the next couple of decades in order to see if fusion is even practical. And only then we will be able to like integrate fusion into our electricity grids. Yeah. So in other words, it's just going to take an extremely long time. Guys, don't expect anything anytime soon, all right? But now that we have come so far, all right, let's at least have a look at what these star machines actually look like. What we are seeing inside is the left half of the tokamak vessel, and the fusion is going to happen in front of your eyes inside jet tokamak. And this is a record-breaking fusion pulse from a couple of years back. So let's see. Now your reaction has started. Your deuterium and tritium atoms are heating up. It is, the temperature is increasing to the order of hundreds of millions of degrees Celsius. It is increasing, and it's gone. Well, that is all that we have so far. That is our best attempt in fusion, guys. Like, we are not that far into this. So Yeah, there's still some hope. Let's see if I come in the next Science Slams. I have some update for you. Thank you very much.